Welcome to Engineering Mechanics Dynamics and this lesson on Rectilinear Kinematics. But before we jump into Rectilinear Kinematics, because this is the first lesson on dynamics, we're going to talk about the two parts to dynamics. Alright, and these two parts are kinematics and kinetics. And so kinetics is the study of the geometry of motion without regard to forces causing the motion, and kinetics is the study of the relationship between the forces on a body and the motion of the body. So kinematics is how the object is moving, and kinetics is what is causing it to move. And lastly, we're going to look at particles and define that. And so that does not refer to tiny specks, but rather bodies that can be considered without regard to size. So when we're looking at objects that we're moving, we'll be considering them particles. And so one example of how this plays out is rotation about the particle's own mass centers will not be considered. And now we looked at rectilinear motion of a particle, and what that means is that motion is in a straight line. Later lessons we'll look at curvilinear motion, and so that's motion not in a straight line. And now let's define some variables. And so t will represent time, s will represent position. You might be used to x in the past. V will represent velocity, and A will represent acceleration. And now to introduce some of the ideas that we will be using. The first is that V average equals the change in position over the change in time. So for example, if you travel 6 meters in 3 seconds, your V average would be 2, oh, I wrote a 3, sorry, would be 2 meters per second. And next, V instantaneous, which is the instantaneous change in position with respect to time. So for an example for this, we have a graph of position versus time. It looks like that. And so let's say this time is 3 seconds and this position is 6 meters. Well, the instantaneous change of position with respect to time right here would be below 1 meter per second. Right here it might be at around 2, and right here it would be well above 2. And so you can see how those change versus the average velocity the whole time would just look like that. And so on average it's going 2 meters per second, but at each point in time it's going a different speed. And the last point to make with velocity is you have this velocity equals the instantaneous change in position with respect to time. If you rearrange the variables, you get this, which will become this. And so this is essentially if you take the slope of position with respect to time, you'll get velocity, the derivative. But if you take the integral of velocity with respect to time, you'll get your change in position. And so you're just going backwards. And so next we have our average acceleration, which equals our change in velocity over change in time. So let's say you go from 0 to 28 meters per second. That's pretty close to 0 to 60 in a car in 4 seconds. well then your average acceleration was 7 meters per second squared. And the instantaneous acceleration equals the instantaneous change in velocity with respect to time. And so we have a VT graph right here, and there's our velocity with respect to time. And so let's say this is 28 meters per second, and this is 4 seconds. At this point, the car is accelerating very fast. But up here, it's accelerating in a much slower place. So its instantaneous acceleration at each time is different, but its average acceleration throughout the whole thing is still 7 meters per second squared. And just like with velocity, you do the same thing here. So if you take the derivative of velocity with respect to time, you get acceleration. And so then if you take the integral of acceleration with respect to time, sorry for the mistake there, you get your change in velocity. So now here's an example problem. A particle travels along a straight track such that position is described by the ST graph. Construct the VT graph for the same time interval. So here's our graph. We have meters on this axis and position or time on this axis. And so it's described right here as s equals 0.5 t to the third. And so the position is a function of time. And s equals 108. And so then to solve this, we need to find a VT graph. And so we have position as a function of time, and velocity equals the instantaneous change of position with respect to time. And so we should be able to use that. And so v equals ds dt, which equals 0.5 t to the third d dt. And then if you take the derivative of that, you get equals 1.5 t squared. And also the 108 d dt equals 0. And now let's draw the v versus t graph. So we have v in meters per second and t in seconds. And so from 0 to 6 seconds we have this slope, and from 6 to 10 we have this. And so let's do that. And to find out what it goes up to, it's at 6 seconds will be its max, and so 36 times 1.5 equals 54. So that's 54 right there. And this slope is 1.5 t squared. And then the velocity immediately goes to 0 for the final 4 seconds. And so there's the answer. Equation. Lastly, I want to show you derived equations that you've seen in physics. And so the material you learned in this lesson can help you get to those equations. So if and only if velocity is constant, so right there you get your constant velocity equation. And if and only if acceleration is constant, you get your constant acceleration equations. Hope this lesson helped you, and this is just part 1 to it. I'll do a second part, so please watch that too. And if you ever have any questions, don't be afraid to ask. Have a great day, and thanks.